Behold, Sagittarius A star, 15 million miles wide with a mass of 4 million suns. It's located smack dab in the center of our galaxy, but don't let this picture fool you. The black hole itself is invisible. You'd be drifting towards this object that's millions of miles wide, and you could never see it. You could only ever see the light swirling around its edge and the space twisting and tearing as it pulls everything in. Sagittarius A star is what's known as a supermassive black hole. And supermassives are sort of a fan favorite, but they're really just one of many different types of black hole that exist. Now, we've been covering black holes for decades at New Scientist. We publish so much about black holes. So today we've pulled together everything our experts know about these mysterious and terrifying astrophysical objects. Part of the reason why we love black holes and why physicists are so fascinated with them is because that's kind of where all our best theories of physics break. Grasping them, really understanding them, will require us to paper over the cracks of physics that exist today. It will require us to reconcile quantum mechanics and gravity, and it will require us to understand space-time like we've never understood it before. There's also something really mysterious about black holes. How do you detect something you can't really see? Maybe we can hear these invisible objects collide over 1 billion light years away. And how could an object known for trapping everything slowly evaporate into nothing? So I hope you join us as we go a bit deeper, because the closer you look, the more unsettling things become. Some black holes were already supermassive when the universe was still in its infancy. Others might be baby black holes, left over from the Big Bang, now hiding anywhere, maybe even in our own solar system, and possibly holding the key to dark matter. And once you get to the center of it all, you'll hit two problems that still haunt modern physics: the singularity and the question of what happens to information when it falls into that singularity. Those are the mysteries that we're going to unpack in this video. We'll cover different kinds of black hole, from the ones we've already observed, supermassives, missing links, and more, all the way through to a wacky assortment of things we think could solve our problems with black holes, like wormholes, gravastars, and these things called fuzzballs. So let's get started. First things first, the basics. Black holes are simple. I'm serious. Now, each of them can be described with only 3 numbers: their mass, their rotation, and electric charge. And yet they challenge our understanding of the rules of which our cosmos is arranged. There are 3 kinds of black holes for which we have strong observable evidence. The most common variety, your garden variety of black hole, is known as the stellar mass black hole. Stellar mass black holes are everywhere. There's millions scattered across the galaxy alone. They form when a star no longer possesses enough fuel to generate this outward pressure and instead succumbs to gravity, first in a dramatic supernova explosion, then collapsing in on itself. Okay, so hold that thought. This is a good time to ask a few basic questions. For starters, what is a black hole? Well, you might have seen a diagram like this before, or have heard Einstein describe space-time like a fabric that stretches and distorts when mass is placed in it. That warping describes how objects with mass all have a gravitational field. Things that travel close to an object fall towards it, rolling across the natural curve of this fabric. Now, only a few months after Einstein published his equations describing this effect, a guy called Carl Schwarzschild found a pretty alarming result. He said that if you had a mass that was big enough, compacted in a small enough volume, it would cause space-time to diverge and just curve into infinity. We call that a singularity. Now, the curvature and gravitational pull of these regions be so strong that light that gets too close to the surface, known as the event horizon, it would just get trapped. And as a result, black holes would appear to us as pits of darkness, like that's why they're called black holes. But they would have these bright, wobbly rings of light around them as light skates across its surface. Now, Einstein was skeptical. To him, this seemed like a mistake, like maybe it existed in the mass of general relativity, but we never really see them. But we have actually observed them. Now, if you imagine an invisible household vacuum cleaner, Even though you could not see the appliance itself, you'd know it was there because bits of dust would react as the vacuum cleaner approached. In this way, beginning in the 1960s, telescopes began spotting black holes by how stars and gases behaved in the immediate vicinity, seemingly orbiting empty space. Since then, our sleuthing abilities and tools have improved. In the mid-1990s, astronomers began tracking the orbits of several stars circling a source of radio waves. And it turned out it was emitted by our good friend Sagittarius A star. The next big leap in black hole detection came in 2016 when the Laser Interferometer Gravitational Wave Observatory, try saying that 3 times fast, aka LIGO, witnessed a collision between 2 black holes. This clash created ripples in space-time. It's precisely the ones predicted by Einstein's theory of general relativity. Fast forward 3 years, and scientists have published a holy grail of sorts, the first ever image of a black hole. In this case, a supermassive. Now, as the name implies, supermassives are like the much larger sibling of stellar masses, and they're not only a little bit larger, they're much, much larger. This brings us on to the monsters living in the middle of our galaxy. Now, a typical stellar mass black hole stretches 30 kilometers wide across its event horizon. That's 15 miles for Americans. As for the Milky Way's resident supermassive Sagittarius A star, try multiplying those numbers by roughly 1 million. The matter contained in black holes is measured in what is known as a solar mass. That's the amount of mass contained in our planet's sun. Now, as the name implies, supermassives aren't just insanely huge. While the mass of a stellar mass black hole ranges from a few suns worth to up to a few dozen, the largest known example of a supermassive black hole contains the mass of our sun 66 billion times over. But it's highly compacted. In relative terms, imagine the entire Earth squeezed down to the size of an object 2.5 centimeters across. That's 1 inch. Like stellar mass black holes, we surmise the existence of supermassives long before we ever even saw one. Over half a century ago, scientists identified these things called quasars. They're the brightest known object in the universe. They speculated that the quasar's blinding light was caused by an amount of heat that could only be generated as matter approached the event horizons of these colossal black holes. As matter enters these supermassives, something known as an accretion disk is formed. This concentrated plasma is propelled by the black hole's rotation. Now, the first ever snapshots removed most of our lingering doubt regarding the existence of black holes, and even more spectacularly, earlier this year, the James Webb Telescope even managed to capture the supermassive within our own galaxy, Sagittarius A star. Now, despite their huge size, these giants are surprisingly common, sitting at the center of nearly every Milky Way-sized galaxy. Astrophysicists speculate that the ubiquity of supermassives could be meaningful, and here's why. We have observed a supermassive black hole formed over 13.3 billion years ago, a mere 500 million years after the Big Bang. That presents an appropriately enormous mystery. Based on what we know about how black holes form, how could one get that big that quickly? Perhaps rather than forming from collapsed stars, these early black holes contained the mass of many accumulated smaller objects, clouds of gas. In that case, perhaps there's a connection between supermassives and the formation of galaxies themselves. In the search for answers to that and other questions, scientists have turned their celestial gaze to the next black hole on our tour, the so-called missing link. Intermediate black holes most certainly exist. The problem, we haven't been able to find many of them. Many speculate that the formation of these intermediate-sized black holes is tied to dense collections of stars known as globular clusters. The hypothesis goes something like this. A single star expires and forms a stellar mass black hole. This then nudges nearby neighbors to collapse and join the party, and a nascent intermediate black hole is formed. intermediate black holes contain a solar mass of approximately 1 to 300 suns. Very big compared to the stellar mass black holes, but a drop in the bucket compared to supermassives. And perhaps drops in the bucket are exactly what they are. Functioning as a sort of galactic food chain, maybe stellar mass black holes combine to form intermediates. Thousands, if not millions of intermediates then are gobbled up to beget supermassives. Hopefully you're still with me, because this is where our plot thickens and acquires a bit of mystery. Hey, it's me in the future. If you're curious about the universe's biggest mystery, there's no better place to look than New Scientist. Our company was formed in 1956 for all of those interested in scientific discovery and its social consequences. And we love to ask the big picture questions all the time about the universe, about life, and what it means to be human. If that sounds like something you like too, then why not join us? With a New Scientist digital subscription, you'll get access to all of our award-winning science and technology journalism, some edited by me, including our daily news so you're up to date with the latest developments, and our deep dive features so you're never without a captivating tale to fuel your curiosity. For a specially discounted New Scientist digital subscription, go to newscientist.com/YouTube. So, back to that mystery. The primordials. Alright, small, medium, and large black holes definitely exist. We've seen them, but we think there may also be an extra small type of black hole, one that might even be key to resolving the mystery of the elusive dark energy and dark matter. So-called primordial black holes could be hiding just about anywhere, maybe even in our own solar system. These baby black holes would have begun forming immediately after the Big Bang. In the universe's earliest days, fluctuations in space-time would have created an uneven distribution in the density of matter throughout the universe, some lumpy bits in the primitive cosmic soup. In areas of relatively high density, micro black holes whose mass would have been able to be measured in single-digit kilograms may have formed. But as if locating primordial black holes wasn't hard enough, like finding needles in an intergalactic haystack, the advanced age further complicates the challenge. Stephen Hawking predicted that black holes emit a type of radiation, what we call Hawking radiation, and as they do so, they steadily shrink. Like melting ice, the smaller they get, the faster they decrease in size. Given the rate of this evaporation, primordial black holes formed shortly after the Big Bang would have already disappeared. The search is now underway for the telltale gamma rays that would represent these ancient black holes' last breath. But quite a lot is riding on it. Many believe that primordial black holes may prove to be the secret hiding place for dark matter, the elusive and invisible glue that binds our universe. But here we come to a bump in the road. What if our concept of a black hole is flawed? As our investigation deepens, additional doors open to an astonishing array of possibilities. Black holes within black holes, secret passageways to travel throughout time and space, and more. All possible solutions to a pair of very big problems. The problem. Be they ultra small, small, medium, or large, all black holes are major pains for physicists. So what was Einstein's problem with them, and why was he so opposed to the idea that they could exist when it was first pointed out by Schwarzschild? Because black holes, as we've described them thus far, break theory, and they present two supermassive problems. Each relates to the idea of a singularity, the points of infinite density believed by many to exist in the center of black holes. In theories like general relativity, infinities are a sign that something is badly broken. Einstein, when he first formulated his theory, relied on space-time being made of a geometry that just smoothly extends. That's how we make the maths of general relativity and energy conservation work. But if it suddenly just veers off into infinity, it's unclear what happens to those other laws. And because of this problem, Einstein attempted, but failed to prove that black holes were impossible. And then there is the information paradox. Originally detailed by Stephen Hawking, this paradox pits our understanding of the physical world in the largest sense against our understanding of the world in the smallest. This is where we get the clash of our two best theories of reality, general relativity and quantum mechanics. General relativity holds that information about matter compressed inside a singularity should just be lost. The problem? The laws of quantum mechanics state that information cannot be destroyed. In tackling these twin challenges, scientists have attempted to tweak the equations and put forth a radical proposal that what we're actually looking at aren't singularities, but are a type of cosmic imposter. They've conjured up blueprints for alternate concepts of black holes in which the maths adds up. This process is known as regularization, and the resulting models are therefore known as regular black holes. But as you're about to see, they are anything but. Here are a trio of cosmic curveballs with quirky names and even quirkier properties. Meet string theory's contribution to the conversation, Fuzzballs. One of the main strengths of the fuzzball model is that on paper, it solves both the singularity problem and the information paradox in one fell swoop. How? Well, string theorists think that reality, every particle in the universe, is actually made up of even tinier vibrating strings and membrane-like structures called brains. They think that a black hole could be a dense tangle of these strings and brains, knitted together in a compact object. To a distant observer, a fuzzball might look like a conventional black hole, but up close, the surface of a fuzzball would be like a weird quantum thicket, a strange vibrating structure, constantly absorbing and re-emitting radiation instead of just gobbling it up. The fuzzball sidesteps the information paradox by getting rid of the idea of an event horizon and singularity. Information never really disappears, it just gets entangled and stored in this mess of quantum strings in the black hole's intricate internal structure. The catch? We all, quite fortunately, live outside of black holes. And from an outsider's perspective, there is nothing which allows us to visually distinguish black holes as understood within general relativity from black holes as reimagined by string theory. The same can be said of the two additional and just as exotic possibilities. Gravastars. Another way to tackle the information paradox. What if, instead of a point of singularity at the center, you have a shell created by a type of repulsive energy? Stay with me here. We know that the universe is expanding, but we don't quite exactly know how. Some speculate that the force driving the expansion of the universe originates from something called vacuum energy. Think of it as the energy intrinsic to the fabric of space-time. Even after you strip away all matter, radiation, and particles that could be in it. Well, what if black holes have a bubble of repulsive vacuum energy at their core, and this region pushes outward, preventing them from collapsing into a singularity? The walls of the bubble would be like an ultra-thin shell of incredibly dense matter, a kind of gravitational membrane. And this is the concept behind gravitational vacuum stars, aka Gravastars. An even more elaborate variation of Gravastars has also been suggested. These are known as knee stars. One Gravastar wholly contained within another, our universe's version of Russian nesting dolls. Or how about something even more outside the box? What if black holes, at least some of them, aren't really black holes at all? This leads us to a name you've likely heard before, but contrary to what you might guess, they're not solely stuck in the realm of science fiction. Wormholes. As seen starring in Hollywood hits like Interstellar, you probably know about the basic concept of wormholes. What you may not know is that these hypothetical tunnels boring through space-time could in some ways mimic black holes. Oh, and also, they could be very real. The idea of secret cosmic doorways bridging the universe past and present may sound fanciful, but their theoretical existence is supported by general relativity. Like fuzzballs and gravastars, wormholes offer an alternative to the problematic concept of singularity. An extremely exciting one. What if something that looks like a black hole from the outside is actually one of these intergalactic portals? In this scenario, some black holes might not be cosmic dead ends, which escape is impossible, but a doorway to something called a white hole, the theoretical yin to the black hole's yang, into which nothing can enter and from which matter spews forth. Even on a theoretical level, a functional wormhole seems fairly far-fetched. One challenge would be maintaining that fragile stability. Ordinary matter has positive pressure and energy, both of which contribute to things like being gravitationally attracted to mass. But to keep a wormhole propped open, you would need something that produces repulsive gravitational effect, matter with a negative energy density. Think of this exotic matter like placing a jack under a car. Gravity pushes the car down, the jack pushes back and keeps the car propped up. For the record, NASA maintains that black holes are not wormholes, meaning the tantalizing, if somewhat terrifying, opportunity to go skipping through time and space will probably not present itself anytime soon. Everything you have learned about black holes may sound totally absurd, and yet both our theories and observations tell us that they truly do exist. We've come to the end of our story, at least for now. The next great frontier, well, that's a proposal to extend our best black hole telescope, the Event Horizon Telescope, into space. The distance between this new explorer and our Earth-based observatories would allow us to capture the most elusive photon rings around black holes in much more detail, providing a clearer outline of space-time at the boundaries where we expect them to break down. The Black Hole Explorer, if funded next year, would launch in 2031. Black holes provide an excellent playground for testing the limits of scientific possibility. They reveal profound truths about our universe and raise even more profound questions. To name but one, can a black hole be destroyed? And if so, do we possess the tools to do it? Could we send it back in time, blow it up with TNT? Well, as our next video explains, if you're going to have any luck, it all starts with moving faster than the speed of light.